everyone. In today we'll be taking the example of aircraft system to design the control using backstepping. So here these are the topics we are going to cover. So we'll take the nonlinear system, longitudinal motion of the aircraft, and also we'll have the MATLAB simulation for the same. So whatever the control will be designing for the system, and I will validate the same in MATLAB. So here, first let's start with the dynamics model example. Let us consider the following simplified longitudinal longitudinal dynamics of an aircraft. The equation of motion we are considering alpha dot equal to q minus L by mv plus g by p cos theta. Simplified model we are considering. Maybe for the different aircraft, we have different equation of motion, but this is the basic one. And q dot equal to total moment divided by Iy, and theta dot equal to q. And here the parameters and states we can define as alpha is the angle of attack, which is in radian, and theta is the pitch angle, and L is the lift force, which is in Newton, and M is the pitching moment, which is in Newton meter, and M is the mass of the aircraft, and V is the velocity, which is meter per second, and I moment of inertia about y-axis, moment of inertia, and C is the gravitational constant. Yeah. And for simplicity, we're using, we are assuming for simplicity, let us assume L equal to half rho v square is CL, and where CL is the lift coefficient, so we can write CL alpha only. We are not taking the other terms. Just for simplicity, we are taking this expression, and M total moment is written as half rho v square is C bar Cm, and where Cm can be written as Cm alpha plus Cm q plus Cm delta I. And here delta is the important parameter, control parameter we are going to design through control, which is going to provide the moment. And our main motivation is how to control the angle, which is theta. So this is the parameter we are going to control through backstepping design process. So here we can write here delta is the elevator deflection, basically the control input. So now our objective is for this particular problem, objective design the control command delta E such that the pitch angle theta tracks the desired reference trajectory, tracks a desired reference trajectory theta dt. Okay, so this is a problem. We are going to solve this objective. So let's start the problem, how we can tackle this to design the control for this dynamics solution. So now let us define the tracking error. Since we have the desired dynamics here, so we need to have the tracking error, and that error variable will be our state of the system, one of the state of the system. So here, let us define the tracking error as z1 equal to theta minus theta d, and z1 dot z1 dynamics, we can write theta dot minus theta desired dot. In place of theta dot, we can write q, right? So we can write q minus theta zeta dot. Now for this equation, our q is the virtual control to control z1 dynamics. So now if we assume, or if we let us define q is the virtual control defined by alpha 1, and let us choose alpha 1 as alpha 1 equal to the same process what you have done in the previous examples, k1 minus k1 g1 plus theta d dot. Yeah. So now let us define, this is 2. Now we can combine the equation 1, 2, combining equations 1 and 2, we can write alpha 1 equal to minus k1 g1 and minus g1 dot plus q, and from this we can write equal to z1 dot, we can write minus k1 z1 plus u minus alpha 1. So this is, we can write from using equation 1 and 2, and let us define this equation by 3. Okay, so you can come up this z1 dynamics using alpha 1 and this z1 dot, and also this equation 2. Now here our main motivation, so if we notice here carefully for this, if q1 equal to alpha 1, g1 will be asymptotically stable dynamics. Now let us choose a Lyapunov function. Let us choose lay upon a function v1 equal to half g1 square, and if we take time derivative v1 dot equal to, we can write g1 dot, and in place of g1 dot we can use equation 3. So g1 equal to minus k1 g1 plus q minus alpha 1, right? And if q1 equal to alpha 1, q equal to alpha 1, we can write v1 dot equal to minus k1 g1 square. So this is basically negative semi-definite. And if you use this condition in equation 3, so we can write, and from equation 3 we can write g1 dot equal to minus k1 g1. So this is basically asymptotically stable dynamics. So now we'll work on for the second variable, g2. So, and g2 we can define using these two parameters. So how we can take differ? This is already we defined in the earlier lecture, because the initial values of these parameters q1 and alpha 1 are different from the different initial conditions, and due to which there can be, we can write the error between q1 and alpha 1, sorry, q and alpha 1, right? So now let us define the same structure we are following from the same concept from the earlier lectures. Let us define the error between q1 alpha 1. We can write g2 equal to q minus alpha 1, and g2 dot we can write q dot minus alpha 1 dot. And in place of q dot, we can write m divided by I y. This is the from the dynamics equation. We have this equation, so we can use there, and minus alpha 1 dot. And in place of m, we can write also half rho v square is c bar cm alpha plus m q plus cm delta I divided by I y minus alpha 1 dot. And let us define this is equation. This is equation number 4. Now we have to choose this in this equation delta I in such a way that G2 dynamics is stable. So now choose delta I in such a way that which makes G2 goes to 0 as t tends to infinity. So here we are choosing delta I as 1 divided by Cm delta I minus Cm alpha minus Cm plus 2Iyy divided by rho v square is c bar minus k to g2 and plus alpha 1 dot. So now if you substitute this delta I expression in equation 4, we can write g2 dot equal to k to g2. So we can write substituting this, or you can write substituting equation 5 in equation 4, we can write G2 dot equal to minus K2 G2. Now let us define a Lyapunov function. Let us. So here we've already found the controls, and also we have shown this is stable. So now we'll check the overall controllability of the system using Lyapunov stability theorem. So now let us choose the Lyapunov function as V2 equal to half G1 square plus half G2 square. And we can take the time derivative V2 dot equal to, so you have to show V2 dot should be negative definite or negative semi-definite. You can write G1 dot plus G2 dot. And in place of G1 dot, we can write G1 minus K1 G1 plus G2, right? So this is easily we can write from this expression. We can write from this expression. Yeah, from this equation. So here we have defined this is G2. So from equation 3, we are writing this expression, right? And plus G2, and in place of G2 dot, we can write K2 G2, right? And from this, we can further write minus K1 G1 square. One more thing in the previous steps, one thing K1 and K2 all are positive. So these are the control gains we are using, and plus G1 G2 plus G2, sorry, minus K2 G2 square. So now using the fact we have G1 G2, we can write less than equal to half G1 square plus half G2 square. Now using this fact, this equation 6 yields, we can write V2 dot less than equal to minus K1 G1 square plus half G1 square plus half G2 square minus K2 G2 square. And from this we can write minus K1 half G1 square minus K2 half G2 square. Now if K1 is greater than half and K2 greater than half, we can say V2 dot less than equal to 0. So this actually ensures asymptotical stability of the system. So now we have done the proof, stability proof, also we have the control, and we can now summarize the full control. So here, control stop, we can write. So delta E we found 1 by Cm delta E minus, this is basically defined here, this equation 5. So this is the overall control, we can write Cm alpha alpha minus CMQQ plus 2IYY divided by rho V square is C bar minus K2 G2 plus alpha 1 dot. So this is the delta E control. And G1 we have theta minus theta dz, and alpha 1 equal to minus k1 g1 plus theta dz dot, and g2 equal to q minus alpha 1. So this is the full control stuff. Now we'll go to the MATLAB code to see how del theta is going to decide some desired value of the pitch angle. So here, this is the MATLAB code for the same. So these are the initial conditions we have taken. This is the initial conditions, and K1, K2, the control gains, we have chosen 2, 3. And the initial condition for alpha, Q naught, theta naught are chosen like this, 0, 0. And desired pitch angle, we have chosen this. And this is the theta dot, theta desired dot. And total simulation time 20 seconds. And this is the OD 45 we have used to solve the OD. And these are for plotting the result. And this is dynamics defined and function, basically aircraft dynamics. So here all the parameter whatever we have used in the this mathematical formulation we have used. This is the desired theta, and this is the error variable we have used, and this is the total control we have found in the through the analysis. And this is the dynamic equation we have, and these are the derivative terms going to the function here. Yeah. So now, if you simulate this code, this is the result we have obtained, and we can see that this desired theta, this is the pitch angle theta, it tracks over times to the desired theta, and this is the blue is the basically actual, and this is the desired one. And other are also controlled. If you notice, other angles also controlled over time. So this is how we can design the backstepping based control for the nonlinear system. For what we have considered in this problem is the longitudinal motion dynamics of the aircraft. So if you have any other dynamical system, you can move like this, and you can design the control, nonlinear control for the same. Let's stop it here. In the next lecture, we'll have how we can come up the control for the lateral dynamics. Thank you.